everyone. So in this series of lecture, today we are going to discuss about the Schrodinger's one-dimensional time-independent wave equation. What exactly the time-independent wave equation is going to give the implication. As we have discussed in the last section that what is the significance of the wave function. So how a particle moving in a potential box is described with the wave function psi. The same wave function psi we are going to take here, and we are going to show that how the particles are going to move in a given volume. That is the probability of finding a particle in any particular volume. Schrodinger in 1926, using the ideas of matter waves, set up a wave equation to describe a new mechanics called the wave mechanics. Schrodinger used Max Planck's equation and quantum hypothesis and partial differential equation of classical wave mechanics. So, because in classical mechanics already a function is described for the waves. So, the same equations here we are going to take, and we are just completely we are going to change it to the quantum mechanics. How we are going to apply the classical wave equation to the quantum mechanics. So, in that series let us describe this particular wave equation. So, in this lecture we are going to discuss about the Schrodinger's one-dimensional time-independent wave equation. So, in the last section we have discussed about the significance of the wave function. So, how Schrodinger has going to describe matter waves by using the wave function called psi of x comma t. The same by using this particular wave function psi, let us see how we are going to set up a wave equation for these particular matter waves. Schrodinger in 1926 itself, by using the ideas of matter waves, set up a wave equation to describe the new mechanics called wave mechanics. So, here he took a new function called psi of x comma t, which describes the motion of the matter waves. Schrodinger used the Max Planck's quantum hypothesis and partial differential equation of classical wave equation. So, because in classical mechanics already a wave equation is set up, the same equation we are going to take, and here we are going to describe the matter waves. How we are going to describe, let us discuss. See. Now, to derive an expression for the Schrodinger wave equation, let us consider a wave function psi of x comma t, which explains the motion of a matter waves. Okay. Now, here I am going to take the psi of x comma t as a sin 2 pi x by lambda. So, this equation we are borrowing it from the classical wave equation, because in classical mechanics already the wave equation was set up, the same equation here we are borrowing it, but the thing is here we are going to modify this equation, classical wave equation, to the quantum mechanically and set up the wave equation for the matter waves. In equation 1, so psi of x comma t is equals to a sin 2 pi x by lambda, where a is the amplitude and x is the displacement and lambda is the wavelength. Now, let us differentiate equation 1 with respect to x once. So, we are going to derive this, differentiate this equation twice, but first let us differentiate equation 1 with respect to x once. So, with that differentiation it comes out to be partial differential equation dou psi by dou x is equals to a, the constant value comes out, that is 2 pi upon lambda into sign differentiation is cos. So, a 2 pi by lambda into cos of 2 pi x by lambda, make it as an equation number 2. Dou psi by dou x is equals to a 2 pi by lambda into cos of 2 pi x by lambda. Now, differentiating equation 2 with respect to x once again, that is twice here we are differentiating equation 1. So, with that it comes out to be dou square psi by dou x square is equals to minus a 2 pi by lambda whole square into, so cos differentiation is sin. So, let me take 2 pi by lambda whole square into sine of 2 pi x by lambda. Make it as an equation number 3. Dou square psi by dou x square is equals to minus a 2 pi by lambda whole square into sine of 2 pi x by lambda. Make it as an equation number 3. But what is a sine 2 pi x by lambda? So we have already taken a sine 2 pi x by lambda is psi of x comma t. Let us substitute equation 1 in 3. So with that substitution, it comes out to be, substitute equation 1 in 3. So with that substitution, it comes out to be dou square psi by dou x square is equals to minus, let me expand this value, minus 4 pi square by lambda square into a sine 2 pi x by lambda is nothing but psi of x comma t. So let me substitute that value and make it as an equation number 4. So equation 4 is dou square psi by dou x square is equals to minus 4 pi square by lambda square into psi of x comma t. Make it as an equation number 4. Now let me rearrange equation 4 as 1 by lambda square is equals to, 1 by lambda square is equals to minus 1 by 4 pi square psi minus 4 pi square psi into dou square psi by dou x square. Make it as an equation number 5. 1 by lambda square. So I am going to use this 1 by lambda square. So let me rearrange equation 4 in terms of 1 by lambda square as, so 1 by lambda square is equals to minus 1 by 4 pi square psi into dou square psi by dou x square. Make it as an equation number 5. But we know that the kinetic energy of the system is given by half mv square, as we know. So these equations are already given in classical mechanics. Let us borrow the same equations from the classical mechanics. So in classical mechanics, kinetic energy is given as of mv square. Make it as an equation number 6. On RHS of equation 6, on RHS of equation 6, multiplying and dividing with m. On RHS of equation 6, let us multiply and divide with m. So with that, it comes out to be kinetic energy, equation 6. Equation 6 is going to be modified as kinetic energy is equals to half m square v square by m. But what is mv? mv is nothing but p. So the same I am going to substitute here, but p is equals to mv quantum mechanically. So make it as an equation number 8. Substitute 8 in 7. Substitute 8 in 7. With that substitution, it comes out to be kinetic energy is equals to half p square by m. That is p square by 2m. Let me write down as kinetic energy is equals to p square by 2m. Make it as an equation number 9. But according to de Broglie's hypothesis, so p lambda is given by h by p. We already derived this equation in de Broglie's hypothesis video. So just go through that particular video. So where lambda is given by h by p, or else the same can be written in terms of p as p is equals to h by lambda. Make it as an equation number 10. Now substituting 10 in 9, it comes out to be kinetic energy is equals to, so in place of p I am going to substitute h by lambda, that is h square by 2m lambda square. So after substituting, so 10 in 9, it comes out to be kinetic energy is equals to h square by 2m lambda square. Make it as an equation number 11. We have already calculated for 1 by lambda square. We have already calculated for 1 by lambda square, whose value is given by 1 by lambda square is equals to minus 1 by 4 pi square psi minus 1 by 4 pi square psi into dou square psi by dou x square. So this is equation minus 1 by lambda square is equals to minus 1 by 4 pi square into dou square psi by dou x square. This is equation 5. So let me recall equation 5 here. This is recalling equation 5. So 1 by lambda square. So this is equation 5. Therefore substituting equation 5 in 11, substituting, so with that substitution, kinetic energy comes out to be, kinetic energy is equals to h square by 2m square. So that is h square by 2m into 1 by lambda square is equals to 1 by 4 pi square psi into dou square psi by dou x square. So minus is here. Let me keep the minus here. So in place of 1 by lambda square in equation 11, I have substituted equation 5, that is 1 by lambda square value is 1 by 4 pi square psi into dou square psi by dou x square. So minus is there. Let me keep the minus here. So make it as an equation number 12. But quantum mechanically, we know that h bar is equals to h by 2 pi. So this is one of the constant introduced by Schrodinger. So whose value h bar is nothing but the h by 2 pi. The same I am going to substitute in equation 12 now. So therefore make it as an equation number 13. Therefore substituting 13 in 12, it comes out to be wherever h by 2 pi is there, I am going to substitute h bar. So with that substitution, equation 12, so I have the value called h square by 4 pi square. So in place of h square by 4 pi square, I am going to substitute h bar. So with that substitution, it comes out to be kinetic energy is equals to minus h bar square by 2m psi minus h bar square by 2m psi into dou square psi by dou x square. Make it as an equation number 14. So kinetic energy is equals to minus h bar square by 2m psi into dou square psi by dou x square. But we know that total energy of the system, is E is equals to kinetic energy plus potential energy. But I have already calculated kinetic energy quantum mechanically. So let me write down this equation in terms of kinetic energy as kinetic energy is equals to E minus V. So where the potential energy, we are going to take it as a capital V. So keep it like that. So it comes out to be kinetic energy is equals to E minus V. Make it as an equation number 15. But kinetic energy we have already calculated. So let me substitute kinetic energy in equation 15. That is substituting equation 14 in equation 15. So kinetic energy is equals to E minus V. So therefore, so kinetic energy is nothing but minus h bar square by 2m psi into dou square psi by dou x square is equals to E minus V, minus h bar square 2m psi into dou square psi by dou x square into E minus V. Or else the same equation can be written as E minus V psi is equals to minus h bar square by 2m into dou square psi by dou x square. Or else the same can be written as E into psi of x minus V into psi of x is equals to minus h bar square by 2m into dou square psi by dou x square. That is E into psi of is equals to minus h bar square by 2m into dou square psi by dou x square plus V of psi of x. This is one form of the Schrodinger wave equation. That is where E is the total energy of the system and this is the kinetic energy of the system and V is the potential energy. That is, this Schrodinger wave equation implies that the total energy of the system is conserved. That is, the total energy of the system E into psi of x is equals to kinetic energy of the system plus potential energy of the system. So where the kinetic energy of the system is given by h bar square by 2m and the potential energy is given by V. So this shows that the total energy of a system is always equals to the kinetic energy and potential energy. That is, the total energy of the system is conserved. So this is what the Schrodinger wave equation is going to imply us. That is, conclusion is the total energy of the system is conserved. The same we can also rewrite this equation of Schrodinger equation as dou square psi by dou x square plus 2m by h bar square into E minus V psi is equals to 0. So this is one more form of the Schrodinger wave equation. So this is the Schrodinger's one-dimensional time-independent wave equation. The same can be written as the three-dimensional way. Schrodinger's three-dimensional wave equation can be written as dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m by h bar square into E minus V psi is equals to 0. This is the Schrodinger's three-dimensional time independent wave equation. That is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m by h bar square into E minus V psi is equals to 0. And whereas this equation is the Schrodinger's one-dimensional time-independent wave equation, that is dou square psi by dou x square plus 2m by h bar square into E minus V psi is equals to 0. So this is the Schrodinger's time-independent one-dimensional wave equation. Thank you.